Hello. Today we're going to be going over chapter 4.7. So, chapter 4.7 is all about bases. It's part of our number theory chapter, which is chapter 4. This these guided notes are quite lengthy because I wanted to make sure that you had all of the information that you needed to be able to do the independent practice and to kind of grasp this topic fully, because it can be a little confusing if you've never worked with different bases. So we do have 7 pages of notes. I'm going to try to make this video not too long, but I do want to make sure that you guys are understanding what bases are, because the next chapter is using bases in different operations, so adding and subtracting. So it's kind of the next section, chapter 4.8, is the last section of the chapter, but it's also kind of it's a level up from what we're doing in today's class. So for the class today, you'll need your guided notes. After class, there's 3 pages of independent practice, but at the end, I put like a little graphic organizer to help you, which will make more sense at the end of class today, hopefully at the end of the lesson. And this same graphic organizer, just in case, is also at the end of the notes. So you have 2 copies, really. You can print as many copies as you need. And I kind of will explain that later. So you have guided notes, independent practice, and challenge problems. I'll explain why these are challenge problems at the end of class. All right, so in order to understand bases in pre-algebra and algebra and even on through calculus, we have to have a good understanding of our base 10. So place value in base 10 is something that we start off learning really early on in like kindergarten. And then we work with base 10 all the way through elementary school. We work with it, everything. It's our number system. So we work with it all the time. But to really understand bases that are not 10, so number systems that don't have a base 10 place value, you have to understand our base 10 place value system. So let's look at the review. Let me just look at things. Hang on. So this is a decimal place value chart. So our number system, there are different number systems that different cultures, different systems use, both today and in the past. We're going to look at that at the next slide. But we use a number system called the decimal system. This isn't new to you. All of this information shouldn't be new. The decimal system that we use uses 10 digits. So we use 0 through 9. Okay. And the place value system says that the value of the numeral, or the value of the number, depends on the placement of the digits in the number. This is true for all base number systems. Specifically in ours, because we use the base 10 system, that means we have 10 digits. So we have, on the left side of the decimal, we have ones, tens, hundreds, thousands, and on the other side, we have tenths, hundredths, thousands, 10,000s, 100,000s, right? As we move from the ones place to the left, or really anywhere, anytime we're starting at a point in the place value chart and moving to the left, we're multiplying by 10. That's what gives us kind of the base 10. So we have ones, tens, hundreds. You've probably seen those, the unit cubes, right? The yellow unit cubes, the 10 sticks, the 100 blocks. You might even see 1,000 cubes. And we can represent the same information down here using a base. Remember when we talked about exponents? So we had a base of 10 and an exponent. So the ones place can be represented by 10 to the 0 power, 10 to the 0. The tens place also represented as 10 to the first, right? Hundreds, 10 to the second. If we evaluated 10 to the second, it equals hundreds, equals 100, right? So it's the hundreds place. Thousands place can be represented by 10 to the third, 10,000, 10 to the fourth, 100,000, 10 to the fifth. So you'll see in both our number system and the other number systems we're going to work with today, the number being represented as an exponent, a base, and an exponent, and also the value kind of like the written out, the standard form of that number. Okay, so we can write numbers in lots of different ways. We're going to focus, or we're going to use the expanded form today. So the expanded form is writing the number by showing the value of each digit. So 817 in standard form looks like this. When we expand it out, we know that this is the hundreds place, this is the tens place, and this is the ones place. So if we have 817, that's 8 times 100 plus 1 times 10 plus 1 times 7, right? That's kind of going back to what we were talking about earlier, where the value of the numeral depends on the placement. So an 8, just because you have an 8 in the number, that 8 could be anywhere. It could be in the 100 spot, it could be in the 10 spot, it could be the 1 spot, but it doesn't actually mean 8, right? It represents something else. If it's in the hundreds place, it represents 800. A 1 in the tens place represents 10, and a 7 in the ones place represents 7. So this is how we would represent that in expanded form. And then when we add those numbers together, we get 817. Okay. So just kind of think about that, or kind of hold on to that thought as we move through. So we talked about how our number system is called the decimal system. It's a base 10. So we have 9 digits, and then after 9, like if we have 9 ones, we get one more, we roll it into the next place value. So if we have 9 here, like when we're regrouping, let's say we have to regroup into the tens place, right? So we work with groups of base 10, 10 to the first, 10 to the second, 10 to the third. Like I said, whenever we're moving this way, we're multiplying by 10. However, there are some different numeration or number systems. Some are ancient and some are modern. For example, in Babylonia, they used base 60. It's believed that they use this because it has many factors. So this is kind of a high-level overview of what they used. They used symbols, and then anytime they moved their place value to the left, they were multiplying by 60. So instead of using 10, they used a base 60 system. Ancient Mayans used a base 20 system. So they used a series of dots and horizontal lines where dots represented a 1 and a horizontal line represented a 5. They might have also used this cowrie shell, I think that's how you pronounce it. They're not sure if they use it as a 0 or a placeholder, but it is seen in their number system. So if they're using base 60 or base 20, that's a lot different than ours, because what they're saying is this place value can hold 59 ones before it's grouped over here. So if they had, actually, I'm not going to go into that. I'm just going to leave that there. So they have 59 ones in this group before it moves over to the next. And this would be represented by just a 1. It wouldn't be a 59 because they're using a different base system. So let's keep looking. So there are a couple peoples in Africa who just recently, I don't know if they still use the base 5 system, but they did until recently. I think maybe the 20th century, I think they stopped using it. They used a common base of 5, and they think, or it's believed that they used a base 5 system because we only have 5 fingers on each hand. So here is kind of a preview into what we're going to be talking about today, where we have ones, tens, hundreds, and thousands. They're using groups of, or they're using base 5, which means this is going to be their ones, this is going to be their 5s. So if they have a number 2 here, that means they have 2 groups of 5, 2 groups of 5 plus 4 groups of 1. So it actually is written a different way in the base 5 system. So it means the numbers are going to look very different when we start writing numbers, or numbers that we recognize in different bases. Okay, so the last one that I have on here is modern computers. So they use a binary system, which is really a base 2. It's the natural number system for use in an electronic computer. So you've probably seen this before. I'm not going to get too far into that because we're going to talk about it later. Okay. So in order to really understand the base, we have to talk about place value, or face value versus place value, which is something I just talked about a few minutes ago. Just get to this page in my notes. So every digit in a numeral or every digit in a number has 2 meanings. One, it has the face value. So if we look at each spot in a number, it's a quantity, right? So for example, in 4,892, this has a value. It's 4, right? But what does that mean? That means it's a quantity 4. We assign a value to it based on its position in the number, which is its place value. So let me erase this. So 4,892, if we line it up in our place value chart, the thousands go in the thousands, right? Hundreds and tens and the ones. So in expanded form, let's go down a little bit. We have 4. This is the face value. But because it's in the thousands place, it really means 4 times 100, right? Another way I've asked students when we first learn about this, like back in elementary school, we talk about what number is in the thousands place. The 4 is in the thousands place. So the face value is 4. But what's the value of that 4? It really means 4,000, right? Okay, next we have, and let me switch colors so I'm not confusing the purple here. So 400. Then we have in the hundreds column, we see an 8. So 8 is the face value, but what's the value of the 8 in the numeral? It's in the hundreds place, so it's 8 times 100. So it's 8. Oh, I'm sorry, this is 4,000. This is 800, right? So 4,000 plus 800. Now we have a 9. The 9 is quantity 9. That's the face value. But where is it in the place value? Place value, it's in the tens column, or it's in the tens place value spot. So that is a quantity 9 of 10. So it's 9 times 10. So that's 90. And then we have a face value 2. We have a 2 in the ones place. So that means we have 2 times 1, which is just 2. So we kind of did it backwards. But if we add up those numbers, 4,000 plus 800 plus 90 plus 2, we get 4,892. Okay, so up until now, I don't think there's anything really new other than kind of the ancient numbers and modern numbers, different number system on the previous page. There shouldn't be anything that's really too new to you. And that's assuming you haven't seen any kind of other base number system before. All right, so now that should be our review. Let's talk about base 10 versus base 5. I'm going to explain it using base 10 blocks, and then we'll kind of go in and look at it a few different ways from here. So base 10, we've been talking about. So thousands, hundreds, tens, right? So this is the first spot in the number, then we move to the left as the number gets larger. So because we're using 10 as our base, we have 10 to the 0. So 10, remember base, from base and exponent. So 10 is our base. So it's 10 to the 0. It's our starting spot. The second spot, 10 to the first. We keep the base the same. Okay, so pay attention to that. The base is the same. 10 to the first, 10 to the second, 10 to the third. It continues on indefinitely into infinity. This would be 10 to the fourth, right? 10 to the fifth. And then as our place value continues to the left, we could assign values to these. So our 10 to the fourth, we could evaluate that. We know that's 10,000, right? So if we have a number in each of these spots, we take that face value, whatever, say we have a 5 here, it's 5, 10. So we know that's going to be 50, right? Plus whatever other numbers are in the numeral. But we know how to find the total number or the standard form of the number by using the base 10 place values. Okay, so I put a little alien here and also a butterfly because I don't know if you've ever heard of a butterfly effect, but this kind of reminds me of that because, and also kind of an alien because it's almost when you learn how to do different bases, it's almost like you have to forget everything that you ever learned about numbers. It's like it's learning. It's like an alien came to our planet and like told us we're not using base 10 anymore. We're going to change the whole way that we think about numbers. Butterfly effect. I don't know, just kind of because it's like, um, it's like just so completely different than what we learned. Like we're learning it, it's very different because we're writing numbers being represented in a different way. So imagine an alien came to our planet and said, actually, we're not going to be using this base 10 number system anymore. So our ones do not mean one. The first value does not mean what it used to. The second value doesn't mean 10. The third number doesn't mean this. We're not going to read numbers the same. It's kind of like turning your whole math world upside down. We start using different base number systems. So if we have a base 5, all that means is we're changing this base to 5. Okay. So this is kind of where the alien comes in because now this place number right here stays the same. So we still have ones, 5 to the 0. This will always be ones in the furthest column on the right. Then instead of this, the second one here, instead of representing 10 sticks, right? These are now 5 sticks. So they're represented this way with these kind of lemony lime sticks. Then we have the 25s. 5 to the 5 squared, 25. We don't use these red things anymore, right? The aliens, so we're not using these 100 blocks. Now we're replacing all of your red 100 blocks with these aqua 25 blocks. And now because we're using base 5, 5 to the third is 125. Our 1000s cube is now 125 cube. So this is how we're going to count numbers, right? So you can still represent numbers. Like if you want to represent a value, you still can. You're just going to do it a little bit differently. Let me see on the next page. Let's see. I think I'll go over on this page first. Okay, so let's say we have the number 29, okay? Well, let's use a little smaller. Let's just do 24. So this would be 24 in base 10. This is the number 24 that we always are used to, right? So if we wanted to represent 24, let's say using counters, we would draw 24 little dots, right? And let me get the stamp. I'll use the star. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. Okay. So what does that mean to me? That means we have a 4 and a 2. That means we have 2 of these and 4 of these. So we have 2 10 sticks. And we have 4 of these cubes. 1, 2, 3, 4. If we wanted to count them all up, we have 24 altogether. If we write that same number in base 10, we get, I'll use green. If we say 20, it's actually written like this, 24 in base 5. So you'll see this down here. If you see a subscript, so be careful, it's not above it, it's not an exponent. If you see a number with a subscript like this, that means it's in base 5. And we're not reading it as 24 anymore. We're reading it as 2, 4, base 5. We'll practice that on the next page. But if we look at the place value, we're going to put that number in to the place value system or the place value chart, but it's just going to mean something different. So 24, this means 2 5s. Okay, so 2 5 sticks. 1, 2. That would be 5 and 5. And then we still have 4 ones, which is like this pinkish peachy color. So we have 1, 2, 3, 4. So to us, it's 24 base 5, but what it really means is 5 plus 5 plus 4. So if we were going to write it in our base 10 system, that would be 14 in base 10. Okay, so in our system, it's 14. If the aliens came, if the aliens came and decided we're going to use base 5, it would be written like this, but it would translate over to this. Okay. Let's look at that on the next page. Just going to take a screenshot of this one. I hope I haven't lost it yet. All right, so we touched on this on the previous page. There's a number written in purple here, and there's another thing written with a tiny little 5 after it. So this is a base 10 number. If it doesn't have a subscript, then we know it's base 10, but you might also see it like this, and that indicates it's base 10. We don't ever write that in everyday life, but we would see it like that if we're working with bases and they want it to be clear that it's a base 10 number. So if we're going to write this in word form, I'm going to type it because it'll be faster. We would say, this is our base 10 number, so we would say 134. Okay. However, if we're reading a number in a different base system, we of course would read it differently. We would say this is 1, 3, 4, base 5. So maybe take a second and think, why do we say 134 base 5 and not 134 base 5? Think about it for a second. Kind of an interesting answer. So we don't say 134 because we're using the base 5 system. That's kind of where it's almost like the butterfly effect, because like if you're looking at 134 base 5, you're like, I swear I used to say this a different way, right? I swear I've seen it a different way before. Why not just use 100? Well, in the base 5 system, the 100 number doesn't exist, and it never existed, and it will never exist. So that's the butterfly effect, kind of, because it's you know that it's true, you know it exists, you know it's there somewhere, but it doesn't exist. It's not real. It only in the base 5 system, or in any other number base besides base 10. So if we're using the base 5 system and the hundreds don't exist, then, and also 34 doesn't exist, because what does 34 mean? 34 means 3 10s and 4 1s, 34. That also doesn't exist in base 5. So if you're using a different base system other than 10, you have to just read the digits 1, 3, 4, and then base 5. Another example, and you might want to try to say this out loud. We're going to talk about base 5s and base 2s in this class, in this section, in this chapter, but you can have really bases of anything. So if you have, let's say, 3 7 2, this would be 3 7 2 base 2. This would be 5 1 8 9 base 16. The only time we use hundreds and 30s and 10s and hundreds and thousands is in our base 10 system. All right, so there's our, just imagine a world where base 10 doesn't exist and base 5 is the only one that does. It's kind of, it would be like if aliens came in and took over a planet and just decided we're no longer using hundreds anymore, right? All right, so building base 10 versus base 5 numbers with the same digits. So we have 134 and 134 base 5. Take a second and think about whether or not you think this is equal. Remember the work we did on the previous page. Do we think those are the same quantities, the same values? We'll get the answer by the end of this page. But let's look. So let's start with our base 10. Okay, we're familiar with our thousands cubes, our hundreds blocks, our 10 sticks, and our unit cubes. So if we were given the number 134 and we were told to put it into the place value chart, it would look like this. We have 100, 3 10s, 4 1s. Let's think back to like when we were first learning about place value in like kindergarten, first grade, second grade, maybe in third grade. And there's your teacher, or if you're homeschooled, your parent or your teacher, I guess, puts down one of the big boxes of all the different assorted place values or place value blocks or base 10 blocks. And they say, build me 134. What would you do? You would grab one red block, right? You would take out one block because you have 100. Then the next number in the tens column is 3. You have 3 tens. So you would take out 3 10 sticks. And then in the last column, the ones, you have 4 ones. So you would take out 4 unit cubes, right? Now you have built 134. Down on the very bottom here, underneath, you can see that in expanded form. So we don't have any thousands, so we don't even need that. We have 100, so that's 100. Plus we have 3 10s. We have our 3 10 sticks, that's 30. And we have 4 ones, our 4 unit cubes up there. So it does equal 134 in base 10. Let's now use, so now imagine you're still in that same class or you're still in that same room and the aliens come and they take your base 10 blocks and they chuck them out the window and they give you a new set of base 5 blocks. And they tell you, build me 100, or no, sorry, not 134, 134. Oh, and you know what? This should not say, oh no, it should say that. I'm sorry. So they tell you to build me 134 base 5. They've given you a whole new set. Now we don't have our yellow unit cubes. We don't have our blue 10 sticks. We don't have our red hundreds blocks. Now they give us this new set with these peach colored unit cubes, 5 sticks, 25 blocks, and 125 cubes. Okay, kind of feels weird. That's the weird part about it. Like, okay, so remember our base is 5, so 5's the first. Now we have 1s, 5s, 25s, and 125s. So if they told us to use these blocks to make 125, we would take this out, right? We would take this one out. We have 125. We have 3 5s, so we would take out 3 10 sticks, or sorry, not 3 10 sticks, 3 5 sticks, and 4 1s, so 4 unit cubes. When we build this, we have built 134 base 5. But what if we want to know what number that is in base 10? We could, and I'm sure we have in our younger years, if we could count up every one, right? We could count every individual little cube because we know that this 25 block is made up of 25 individual units. We know this one has 5, 5, 5, right? And this one is 4. So if we put them all together and counted every little tiny cube within each block, or each stick, then we could find what the answer would be in base 10. Or how many, what the quantity would be. However, we want to do it using expanded form. So just like we did before, we're going to write it out. So our 134 does not have any 125, so it's just a 3-digit number. We have a 1 in the 25s column, so it'd be 1 times 25, that's 25. We have a 3 in the 5s column, so that's 3 times 5. And we have a 4 in the 1s column, so it's 4 times 1. So 25 plus 15 plus 4, that would give us 44. So the number 134 base 5 is equal to 44 in base 10. You could put that like this. You could leave it off because we know that if it doesn't have a subscript, that it is equal to the base 10. So 134 base 5 is a quantity of what we know as 44. I know it's kind of a lot to wrap our head around. But that would be, if you get asked the question, write 134 in base 10, that's how we would do it. We would do it exactly how we just did. We would make the place value chart, just like we always have when we're doing place value, except we're assigning different values. The column all the way to the right. So if we start with this first column and work our way to the left, first column is 1s, then 5s, then 25s. All right. We're more than halfway done, I think. Yes. Feel free to take a break if you need it. I know this could be kind of tricky. Worth it. So we talked about base 5s. Now let's talk about base 2s. So anytime if you are interested in computer programming or really any kind of computer science, you'll use binary systems. You'll use base 2, you'll use base 8, and also base 16. Technically we use base 60 when we talk about time, right? Think about time. We'd start with the seconds. We have 60 seconds. What happens after the 60th second? It rolls over into a minute, right? And what happens after our minutes run out? Then our minutes go over into hours. So that's technically a base 60 system. Our 59 seconds rolls over into 1 minute. And then so on and so forth. We just keep regrouping however many times we need to. All right, so let's look at base 2. Even today, bases other than 10 are used frequently. Computers run on a binary or base 2 system. A computer's electrical impulses are either off or on. And a computer program represents these two possibilities by a 0 and a 1. The binary system only uses, this is where my keyboard was dying last night when I was making these notes. And it was only typing half the words. The binary system only uses these 2 digits. So if it's base 2, we have 0 and 1, which is where, if you look back, let me scroll back up. You've probably seen this like in somewhere. You've probably seen this kind of code. Whether or not you've worked with it, you've probably seen pictures of it either in movies or TV or somewhere. That's the binary code. Okay, so with the binary system, you start with the 1s, right? So your base is 2, so you have 2 to the 0, which is 1. 2 to the first, which is, we evaluate that, it's 2. 2 to the second, 2 squared, we evaluate that, that's 4. 2 to the third, that's 8. 2 to the fourth, that's 16. So instead of thousands, hundreds, tens, blah, 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 like in base 10, we have 1s, 2s, 4s, 8s, 16s. To help give you a visual, here's our base. These are base, I should put like this, base 10 blocks, because they're really not base 10 blocks, they're base 2 blocks. If you want to write base 2, that would probably be helpful. So we have 1, 2, then 4, then 8. than 16. And 16, I couldn't find a picture of that one because it doesn't exist really. Okay, so let's try some. The question is, let's write 101 base 2 in base 10. So there's a process to do this, and it's going to be the same kind of every time. So if you need to take a number that's not in base 10, so a number, some other number in a different number system, and write it in base 10, you have to start by using the place value chart. So set up a place value chart for base 2. Let me see if I can do that. Not vanishing pen, smart pen would work. All right, so kind of like what we already have. How many do I want to do here? You can use the one above, I guess. But we're going to do it like this. My lines are not straight. I wish Zoom would come out with a table feature and annotate. That would be really good. Okay, so what we would do is you want to do your place values. Starting with 2, 0, and then 2, 1, and 2, 2. So the value of 2, 0 would be 1. 2, 1 evaluated would be 2, and 2, 2 evaluated would be 4. Okay, then this is step 1. Step 1 is to make the place value. Then you need to put in the face value of the numeral that they gave you, which is 101. So we're going to put that here. We're going to line it up in the chart. 101. Then step 3 is to write that numeral in expanded form, just like we did before. So we're going to be multiplying these two numbers together and adding them. So 4 times 1 plus 2 times 0 plus 1 times 1. So that comes out to be 4 plus 0 plus 1, which equals 5. And so we could say that 101, see, a bad habit, 101 base 2, or 101 in binary code, equals 5 in base 10. That would be our answer. So if we wanted to program a computer, like maybe one day you want to be a computer programmer, you want to program the computer at some point, you would, if you want to tell the computer 5, you would have to enter 101. To us, that looks like 101, but to the computer, it means 5 because they only use the binary code. The bottom. I know this video is quite lengthy, and I apologize, but there's a lot that goes into this. Okay, this one says write 34. Nope, see, I did it again. Write 3, 4 base 5 in base 10. We're going to do the same thing that we just did above. So maybe try to pause and see if you guys can do this on your own and then come back for the answer. All right, step 1, set up the place value chart. This time we're going to set up the place value chart for base 5. Okay, so let's see, we have 3, 4. So if we have 3, 4, that means we're only going to need 2 place value spots, right? So it's going to be 5, 0, 5, 1, 5, 2. There's only 2 spots, so we're only going to need this and this. If it was 5, 3, 4, 1, 6 base 5, then you know you're going to have the place value chart is going to have 5 columns, but we have a pretty short number. So set these up and then assign their values. So 5 to the 0 is 1, 5 to the 1 is 5, 5 squared is 25. Now step 2, is to put in the base value. Just like when we do base 10, we're going to start all the way to the right. Okay, so the 4 and the 3. Now, step 3 is to do write the numeral in expanded form. So we're multiplying this, and then adding together. We have 5 times 3 plus 1 times 4. Oh, and there goes my haunted pen. 4. So that's 15 plus 4, which equals 19. So 3, 4, base 5 equals 19 in base 10. All right, now let's say we want to go the other way. We want to change a base 10 numeral into other base. So let's say we have a number that we want to program into the computer, into our computer program, but we need to put into binary code. How do we know how to do that, right? The place values of the place you're changing, the place that you're changing to, will be needed to do this conversion. There's a lot of text right here. You can read it on your own if you want. I'm not going to read it because it just comes out like blah, blah, blah anyway until you see it in action or see it in an example. So let's say, okay, so here's a good example. We want to tell the computer the number 28, our base 1028. We want to translate it into the computer's code. How do we do that? Let me go to that page in my notes. Oh, no, I'm in another spot. Yes, okay. So, the first step, like you can read along above, the first thing you want to do is make that same place value chart. So we're going to make a place value chart for base 2. So we're going to do place value like this again. We're going to do another column. And then we also have to do kind of like a face value or a numeral row. So in the previous page, we knew how many columns we needed because we were we knew based on like the 3, 4, base 5, we knew that we only needed 2 columns, right? In this one, we're not going to be sure until we kind of how to evaluate, but until we fill out this row here. So I would start with maybe 5 each time, where this is going to be 2, 0. Let's put this one here. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, whoop, 2, 4, 2, 5. Okay, but what does that mean? We have our base 2s. This is going to be 1, 2, 4, 8, 16, 32. Now, if you read up above, it says the highest place value less than or equal to the base 10 number must be divided into the number, determine the number of times, blah, 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 right? That's the first column up, that first bullet point. What that means is you want to look at this number and find a spot where it belongs. It might be exactly the base. It might be exactly one of these numbers. If it is, great, perfect. If it's not, find a number that's in between. We can't use this number because that's too much, right? But however, we can use this column because 16 is less than 28. So we don't want to use this, that's too much. We want to find the in-between or the exact. So that's why it says less than or equal to. So if we're starting with 28, and I hope you're good at long division because that's going to come in right here. That is the second part of the first bullet point. The must be divided into the number to determine the number of times that power appears. So what you're going to do is you're going to start, so we know this is nothing. You're going to start with 28 and you're going to divide it by 16. 16 goes into 28 one time, and we subtract and we get 12. Okay. So it went in once, so that's going to go here. Now we move to the next column. Now we bring our 12 up here, and we're going to divide it by 8. divided by 8. How many times does 8 go into 12? Once, multiply, and we get 4. So 1 goes here, and we move on to the 4. So then we take our remainder, we bring it up here, and we divide it by the next value. So 4 is our remainder, and we're dividing by 4. 4 goes into 4 once. That's 4. Remainder is 0. This, I wish I could set like a little bell off, like ding, 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 because now our remainder is 0. Once we get 0, we're going to put a 1 here. The other columns, we don't have anything left. So these are going to be, the other columns are going to be 0. Make sure you put zeros there, because although base 5 is, or base 2 and base 5 are different than base 10, we can't leave these blank if we have numbers over here. Okay, so just because, like, if we have in our number system, if we have let's say 3400, it's 3000s, 400s, 010s, and 01s. We need these here because because we need those there. We can't just take them off. That's a completely different number, right? Same thing here. We need to put those zeros there, because if we don't, then we're going to write it as 111, and that's a completely different number than 11100. So be careful. All right, so once we get a remainder 0, fill in the numbers there, and then that becomes our number for base 2. So 28 equals 11100 in base 2. Okay. This is going to take some practice probably to get used to. All right, write 43 in base 5. Same thing. You might want to pause here and try it on yourself. If not, that's okay. So we're going to go place value. We're going to make our place value chart. That's step 1. So for this one, I'm going to make 1, 2, 3. So we go 5, 0, 5, 1, 5, 2, 5, 3. This is going to be 1, 5, 25, 125. This is our face value. So we're representing 43 in base 5. So this would be too much. This is not enough. So it's right here in the middle. Okay, so that means we're not using this. We're going to start by dividing 43 by 25. It goes in once, 18 left over. So because we have a remainder, we're not done yet. We have to go to the next column. This, though, is going to be 1. So we have 125. Bring this over. Now we're going to do 18 divided by 5, because 5 is next. 5 goes into 18 3 times. We still have a remainder. We don't do anything with the remainder yet. We're going to write 3. Now we have to do the ones. So this one, 3 divided by 1. 1 goes into 3 times. Remainder 0. So ding, ding, ding. Remainder 0. This is 3. This is 3. So 43 equals 133 base 5. The last one I put in there in case you wanted to try some of the challenge problems that I gave you for homework, because we're not really focusing on base 3, but you can write any base 10 number in any other base system. So it would be the same as what we've been doing previously, where you write the place value if this is 3, 0, 3, 1, 3, 2. 3, 3, 3, 4. So 3, anything to 0 power is 1. Anything to the first power is itself. 3 squared, 3 times 3, that's 9. 3 cubed, 27. 3 to the 4th power, 81. So same process. We need to find the face value. So we have 27. So remember, less than or equal to. So 81 is too much. It actually comes out to, it's exactly 27, right? So if it's exactly 27, you could do it out if you wanted to. It goes in one time with no remainders. But if it's exactly that number, then it's just going to be 1, and the rest are going to be zeros. So 27 in base 3 is 10003. All right. So now going over to the homework. I gave you this graphic organizer here. Let me pop over to the homework first. So there's 3 pages. The first page, you have to take the number from base 5 or base 2 and put it into base 10. Second page, take the base 10 numbers and put it into base 5. And the third page, take the base 10 numbers and put it into base 2. So we did all of those examples in class in this video. If you're stuck, go back and look for a similar question in the guided notes that we did together, or look back in the lesson or the video, and it should, you just follow the steps that we did in the problem. All of the questions that are on independent practice are exactly the same questions that, type of questions that we did in class in the guided notes. So with these, that's why I put these in here, because you can use this. You might want to print more than one copy or write it down more than one time, because they'll help you to put the, like if you have the face value of, let's see, which page would it be? Let's see, you're doing face value of base 2. So if you have this, right, 1, 1, 1, 1, 1, 1, 1, base 2. Come over here to your notes, to the base 2. Plug it in, 1, 1, 1, 1. That's your face value. 1, 1, 1, 1. And then do expanded form and then figure out the answer. So 8 plus 4 plus 2 plus 1. That'll give you the answer. Okay, that's why I said you might want to print out more than one copy or write it down more than one time, because you can use this for that. Same thing for base 5, the same type of question. You can go the opposite way as well. So if you need to write 64 base 10 in base 5, this will help you to do that as well. Instead of writing it out every time like we just did, we're finding 64 in base 5. So look, it comes right in between here. It's already written for you. You don't have to write out that whole place value. So that'll help you. That'll hopefully make it a little bit simpler for you. The challenge problems are basically taking the base 10 numbers and writing them in different, write the following numbers in base 10. So you have 735 base 8. What does that equal to in base 10? That's like, actually, it might not be quite like the one we did in class. It's opposite of what we did here. So for the challenge, you will have to use a similar process to these. Okay, so you'll have to write a place value chart for base 8, and then write in the face values for the 3 columns, and then use expanded form to find out what it would be in base 10. All right, and I can do a separate video if you want some help on those. All right, I apologize in advance for the length of the video. I hope I didn't drive you too crazy. I hope that you guys understand bases. Like I said, it's important to understand this before we really move into chapter 4.8 next week, or next time I see you, depending on where you are in the schedule. Let me know if you have any questions, and I will be around to help you if you guys need it. Okay, I will see you next time.